Hello there. Here's the start of our Calculus 1 review. So we're going to begin with limits, and then we're going to take a look at derivatives, follow that with some applications of derivatives, and finish off with some integration. So we're going to begin with evaluating the following limit. Limit as x approaches 4 of x squared minus 16 in the numerator, divided by x squared minus 7x plus 12 in the denominator. And the first thing to do whenever you're encountering a problem like this is actually to just plug in the value. But when we plug in the value here, what we have is 16 minus 16, which is 0 in the numerator, and then we'll get 16 minus 28 plus 12, which is 0 in the denominator. And there's a couple ways to do this. For those of you that have seen L'Hopital's rule, you can use that method. That works just as easily. Let's actually go through though what it means if we have 4 plugged in. It's good to get practice with this factoring as to what's going on. So since we plugged in 4 and we got 0, this means we can factor the numerator. You get x minus 4 up in the numerator, and then another x plus 4 is what x squared minus 16 factors to. In the denominator, we know an x minus 4 must exist as a factor, since when we plugged in 4 we got 0 once again. So we get x minus 4 times, well, we want to have a thing that makes a product of positive 12, and when you add the two numbers it's negative 7, so that means this has to be a negative 3. So what can we do here? Well, this allows us to just cancel off these terms, just right here, like so. And so what we're left with is limit as x approaches 4 of x plus 4 over x minus 3. Okay, so now with that in mind, how do we proceed from here? Well, we can now try and plug in 4 again. So when we plug in 4, we can drop that limit symbol, so we are left with 4 plus 4 divided by 4 minus 3, and so notice that equals 8 divided by 1, which is just 8. So graphically, what does this mean? Well, I'm not so certain what the graph of x squared minus 16 over x squared minus 7x plus 12 is, but what I do know from this information, notice we're taking a limit as x approaches 4, and then we get some value of 8. So what that means in terms of our graph, when we go 4 units to the right, and 1, 2, 3, 4, 5, 6, 7, 8. What's actually happening here? Well, when we plugged it into our original equation, it wasn't defined. However, when we plugged it in for the limit, we got a value. And so what that means, I'm not sure if this is an upward trend or a downward trend. So you get either something like that, or 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. And so the other sort of way it can go, you have a hole at 4, 8. So in either case, I don't know which graph it would be off the top of my head. We can figure that out actually. But the hole is at 4, 8, and in this case, same thing. You have a hole at 4, 8. So it's going to be one of these two scenarios. And notice all we did is just calculate that limit, and that gives us that information. Okay. Hopefully that helps with that problem. If you have any questions along the way too, please feel free to. There should be a chat on the right-hand side. Feel free to chime in and just let me know your questions, and I'll try and answer them as they kind of come in. Okay, next problem. Evaluate the following limit. We have the limit as x approaches infinity of 9x squared minus 7x plus 8 in the numerator. And down in the denominator, there's a 4th root of 81x to the 8th minus 13x plus 2. Okay, so how do we proceed on this one? Well, we have an infinite limit. You can try and plug it in, but notice we get infinity minus infinity when you plug in for the 2x's in the numerator. Same thing down below. That tells us a whole lot of nothing. So how do we proceed? Well, there's a few tricks to this. And what we'll try and do is we'll look at the degree. And usually we look at the degree of the denominator, but with that 4th root it might be kind of nasty. So we'll say 9x squared minus 7x plus 8, and down below we still have that 4th root of 81x to the 8th minus 13x plus 2. What we'll do though is we'll group in, let me just erase that little piece. a few different ways. You can factor out an x squared in the numerator. You can factor out an x to the 8th of all the terms in the denominator, see what happens that way. The way I prefer to do it myself, I multiply the numerator and denominator by 1 over x squared. And yx squared, well, that happens to be the degree of the numerator in this case, since the denominator is kind of funky looking. Okay, so when we multiply that on through, what do we have? Well, the numerator will be easy, and remember we have to multiply it times each term. Most people just multiply it by 1 and they forget about the rest. So 9x squared times 1 over x squared gives us 9. 7x times 1 over x squared will give us 7 over x, and plus 8 times 1 over x squared is 8 over x squared. Okay, and we still have our denominator. We're going to need to rewrite it slightly, and so when we have our 4th root of 81 x to the 8th minus 13x plus 2, instead of writing 1 over x squared, we need to make that a 4th root. So in order to make that a 4th root, the way you do that is you take a 4th root of 1 over x squared, but you need to raise it to the 4th power, because the 4th root of something raised to the 4th power is just what you have there. And so that makes it the 4th root. This will become, just a little FYI, rather than rewriting this whole step, this is just the 4th root of 1 over x to the 8th. Okay, and I see some questions popping up there. I'll address those after we finish this problem. So going back to the first problem, how do we know it'll be a whole? We'll be able to solve that in just a second too. So limit as x approaches infinity on this one. What actually happens? Well, you get 9 minus 7 over x plus 8 over x squared. And now, since our roots match, since we have two 4th roots, we can actually multiply what's inside the 4th root on the right hand side into that other 4th root on the left hand side. So 81 x to the 8th times 1 over x to the 8th just becomes 81. 13x times 1 over x to the 8th becomes 13 over x to the 7th. Okay, and then 2 times 1 over x to the 8th just becomes 2 over x to the 8th. And now we're ready to proceed with actually evaluating this limit as x approaches infinity. So what we have is 7 over x. The limit as x goes to infinity of that thing. So this piece, this will go to 0. Because as x gets really large in the denominator, the 7 really won't matter much. So you get that whole thing goes to 0 as x goes to infinity. 8 over x squared as x goes to infinity, that goes to 0. 13 over x to the 7th, and remember the x is in the denominator, so that takes that whole thing to 0, and 2 over x to the 8th, that will take that whole piece to 0. So what we're left with is the limit as x approaches infinity of, so we have 9 minus 0 plus 0 over the 4th root of 81 minus 0 plus 0. So this is equal to 9 divided by the 4th root of 81. And you might not know the 4th root of 81 off the top of your head, but it might be a little bit easier. 81, if you notice, is 9 squared, and 9 squared is 3 squared, essentially. So you could write this as the 4th root of 3 to the 4th, and notice the 4th root and that 4th power will cancel, and so this means we have 9 over 3, which our answer is just 3. Okay? So what does that mean in terms of the graph as to what's happening? Once again, we have this crazy function sitting here, and we could actually work and try and figure out where the values are and all that jazz. But at the end of the day, what you have is this is your x and this is your y. If we go 1, 2, 3, we're going to have one of two things occur. Okay, so this is y equals 3. As we get out, way out, further and further, I don't know if it'll cross this or not, but at the end of the day, you'll have either the graph approaching y equals 3 from this side, or you'll have, as we approach infinity, so this is y equals 3 once again, this is your x-axis, and that's your y-axis, you'll have it approaching y equals 3 from this side. So essentially we know that this infinite limit, what is it telling us? It's telling us that we have a horizontal asymptote at y equals 3. So you have a horizontal asymptote at y equals 3 since we calculated that infinite limit. So we had a question actually back on the first problem, and so I'm going to reroute it real quick back to that first problem. So how do we actually know that this graph is a hole, has a hole there? Well, so what we know is that f of x equals x squared minus 16 over x squared minus 7x plus 12 is undefined at x equals 4. And the reason why, when we plugged in 4 into our denominator, we came up with a 0 down below. And you can't divide by 0. So, since it's undefined, we have some form of a discontinuity there. So there's 3 types of discontinuity. There's an infinite discontinuity, a jump discontinuity, or essentially a hole or a removable discontinuity. Well, it's not an infinite because we found our limit to be 8, right? And it's not a jump because a jump discontinuity would talk about you have 2 sides that aren't equal, right? You'd have a left-hand limit and a right-hand limit, and they're different values. Since we found that this value is 8, this tells us that this is a removable discontinuity, or it's a hole in the graph. Okay, hopefully that makes sense and answers that question. Please, I strongly encourage you to continue to ask questions as long as you have them. I'll be here to help out there. Okay, so we got this infinite limit, understanding that infinite limits and horizontal asymptotes coincide with one another. Let's move on to the next problem. So something a little bit different. Evaluate the following limit. Limit as theta approaches 0 of theta cubed times cosine of 1 plus 7 theta squared up in the numerator divided by a 4 theta. Okay, how do we actually tackle this problem? Well, what we actually do, this case you can plug in first, and you'll see you get 0, but then we get something 1 divided by 0. Who knows what the heck that's doing in terms of the inside of the cosine. And you can type that into a calculator. Good luck with that, too. It's not going to do much work for you. So what we do, there's a couple methods that we can try and do. One is we try and work with trig functions in terms of one of the trig limits and things of that nature. But actually, there's a better theorem in this case. The cosine, it's a nasty function, but we have this cosine is actually bounded. And so what we're going to do, we're going to try and use what's called the squeeze theorem. So see something a little bit different. And so cosine, regardless of what values it is, we know that on the inside, regardless of what we have, we're going to have the cosines bounded between -1 and +1. Okay? Anytime you have a cosine function or a sine function, those two are always bounded by -1 and 1. So now what we'll try and do is match the function that we have right up top here. So the way we do that is multiply every term in the inequality by theta cubed. So that we get negative theta cubed is less than or equal to theta cubed cosine of 1 plus theta 7 theta over 4 theta, and is less than or equal to theta. I should probably put a little disclaimer here. The inequality would switch if theta is actually a negative value. That's not going to make much of a difference in terms of what we're getting at the end of the day, though. So we'd have to switch the inequality if theta is less than 0, approaching from the left-hand side, and so you'd have negative theta cubed. In that case, is greater than or equal to theta cubed cosine of 1 plus 7 theta over 4 theta, and that's less than or equal to theta. But either way, what we can do now is let's take this limit as theta approaches 0 and see what happens. So you get limit as theta approaches 0 of negative theta cubed is less than or equal to the limit as theta approaches 0 of theta cubed cosine of 1 plus 7 theta over 4 theta and is less than or equal to, oh, I'm sorry, I forgot the theta cubed there. And the limit as theta approaches 0 of theta cubed here. And if we wanted to fix that so we didn't have to switch signs, by the way, I'll show you how to do that. That's not too hard. We can just put an absolute value here and an absolute value there. So we know the left-hand side is always negative and the right-hand side is always positive. I don't want you to get too confused on that part. That's not the important piece. It's keeping that in mind. So now, with that in mind, we have this function always bounded between these two values. But the left-hand limit as theta approaches 0 of negative theta cubed, whether it's absolute value or not, you get 0. And the right-hand limit as theta approaches 0 of theta cubed is 0. So notice this limit has to be a number between and possibly equal to 0 and 0. Well, the only number between 0 and 0, what do we get? Well, we get the limit as theta approaches 0 of theta cubed of cosine of theta, or cosine of 1 plus 7 theta, divided by 4 theta. That has to equal 0. And the reason why is by the squeeze theorem. Okay, so basically we squeezed it in between two numbers, those left-hand and right-hand limits. They actually came to be the same number, so it's the squeeze theorem that we used to get our final answer. Okay, moving on to the next problem. If there's no other questions there, let's take a look. We want to determine all values of k such that f of x equals kx squared plus 4 if k is greater than 1, and k plus 10x if k is less than or equal to 1. And we want to determine all values where it's continuous. So continuity, you need a few things. So f is continuous. Let's recall here. If the limit as x approaches a of f of x equals f of a for all real numbers a. Now for this problem, what do we need to have happen? Now some of you might just plug in, oh, I made a mistake there and I'm writing it up, sorry, my apologies. I wrote k greater than 1 and k less than or equal to 1. We want x to be greater than 1 and x to be less than or equal to 1. Sorry about that. So hopefully that's a real quick fix there for you. And the reason why we want x defined over there is because x is our variable. K is the value that we're going to try and find. So now, if we take a look at this, how do we actually go about solving it? Well, first off, we need a limit to exist. In order for a limit to exist, and where's the problem point going to be? Well, notice we can plug in anything greater than 1 and anything less than 1 into this function, and it'll always work. The key point is when it equals 1, because that's when we have this limit might not exist. So that's the only point we really need to check. So we want the limit as x approaches 1 from the left of f of x to equal the limit as x approaches 1 from the right of f of x. Okay, and the reason why on this is because we need that left-hand and right-hand limit to actually be equal in order for the limit to exist. So what does this mean? Well, limit as x approaches 1 from the left. 1 from the left would be when x is less than or equal to 1. So this is essentially just limit as x approaches 1 from the left of k plus 10x. Okay. And the limit as x approaches 1 from the right, what's the function we're dealing with from the right? That's going to be the x greater than 1. So that's going to be k squared times x plus 4. Okay. So now, taking a look at this, what do we have? Well, we have k plus 10, we're just plugging in for x, times 1, equals k squared times 1 plus 4. Okay. Now, so we have k plus 10, we have a k squared, so notice we can write 0, we're solving for k now, equals k squared minus k, and then when we subtract 10 on over, that'll be minus 6, I believe. Okay, so if you take a look at this, this can be factored. So you get 0 equals k minus 3, k plus 2, right? And so what we get is k minus 3 equals 0, k plus 2 equals 0, which implies that k equals either 3 or negative 2. Okay, now you might say, oh, but Josh, there's one last check here. Yes and no. Notice that in our first scenario, x less than or equal to 1, this value, so for the one from the left, that actually corresponds to f of 1. So we automatically have the equality f of 1 equals the limit as x approaches 1 from the left of k plus 10x. So we already actually took care of that other scenario all in one step. So you might have cases where you have a third scenario where you'd have a left-hand limit, a right-hand limit, and an equal to some certain value at a certain point. Then you'd have to do that check as well. But at the end of the day, for this problem, we were just lining up. And what we did essentially is just plug in the x values, make sure they lined up perfectly. So seems like there's no questions on that one. So we'll continue moving forward after the continuity. What actually happens then? Oh, we're on to derivatives, the fun stuff. So find the derivative of f of x equals the arctangent of e to the x times the square root of x. So just in case we didn't know, let's have a refresher here. What is the derivative of the arctangent of x? So the derivative of arctangent of x, so let's write, now notice we don't have an x on the inside, so that means we're going to need to use something else. But derivative of arctangent of x is 1 over 1 plus x squared. If you don't know where that comes from, you can let me know. We can draw a triangle and come up with that whole formula. But at the end of the day, that's what you get for your derivative of arctangent of x. Okay, other components we're going to need here, we're going to need to know the derivative of e to the x, which is just e to the x. And we're going to need to know the derivative of the square root of x, which there's a couple different ways you can do this. So some people know right out the gate it's 1 over 2 squared of x. If you don't know that, another way to have written this is d dx of x to the 1/2, and now you can use your power rule, so that becomes 1/2 x, and then this goes 1/2 minus 1, which is just negative 1/2 up there. But notice that that's 1 over the square root of x, so this becomes 1 over 2 square root of x. So they happen to equal, surprise, surprise. And then the one last piece that we're going to need to use here, notice that when you have an e to the x and a square root of x, we're taking a product of two functions. So that tells us that we are going to need to use a product rule. So the derivative of f of x times g of x equals f prime of x times g of x plus f of x times g prime of x. Okay, so those are all the components we're going to use. I wouldn't recommend actually going through all those steps unless you really feel you need to. It's not necessary, but I just want us to see, and we can pull all these pieces here. So we have all the derivatives. So when we do f prime of x, how do we start this? Well, we start with the outermost function, which is the arctangent of x. We're going to take the derivative of that. So usually that's 1 over 1 plus x squared. But we've changed and replaced this x with something. So it goes 1 over 1 plus, and instead of x squared, we now have e to the x square root of x. So you have e to the x square root of x, and that whole quantity is squared. Now, what we need to do is, this is a chain rule, so I'll just write derivative for right now. Derivative, so this is supposed to be multiplied by the derivative of e to the x times the square root of x. Okay? So rather than try and do it all in one step, we can just break it down piece by piece. And so now we have equals 1 over 1 plus. If you want to get fancy with it, you can. It's not necessary, but we can take the 2 and multiply by both of those. Remember, square root of x squared is going to just be x, and then e to the x squared is just going to be e to the 2x. So this is e to the 2x times x, and then times, well, we need to use this product rule. So product rule, what do we have? We take the derivative of the first times the second, so times the square root of x, plus, hopefully I can fit this all on the page here, e to the x times the derivative of the square root of x. Ooh, I made it. Yay. Okay. And hopefully we can see all that. So, in terms of where we go from here, what do we have to have happen? And so we can write this as 1 plus x e to the 2x times derivative of e to the x is just e to the x, and you have a square root of x right there, plus our next one is e to the x, and then our derivative of square root of x is 1 over 2 times the square root of x. We can close that thing off right there. Now, a couple ways to go from here. So you can leave it like this most of the time, unless there's, like, say there was a multiple choice question and you had to simplify or something like that. If you had to simplify, what usually happens is they want to try and take care of this denominator, and in that case there's a little trickery that goes on here. So first off, let me write this in the numerator. You get e to the x square root of x plus, and this becomes e to the x over 2 times the square root of x, all over 1 plus x e to the 2x. So notice that denominator up top, so the way to fix that is you just multiply both the numerator and denominator by 2 times the square root of x. Okay, and when you do that, what happens? Well, you get the square root of x times the square root of x gives you x, so you can rewrite the first part of the numerator as 2x e to the x. The 2 square root of x will cancel, so plus e to the x, all divided by 2 square root of x times the quantity 1 plus x e to the x. And some other forms you might have is you might factor out an e to the x in the numerator or things like that, but you can continue to keep on doing that. Now, so we had a question on the test: will you be doing what you just did, just knowing certain derivatives work, or will we need to show how to solve each like I did with the square root of x? No, there's no need to show that you have the derivative of square root of x down. I'd hope that you have that down, or if not, you have a list that might help you in some form or another. So thank you. Yeah, that last bit, e to the 2x, that's correct. Good catch, Jay. I appreciate that. So yeah, it's x e to the 2x. Yeah, thank you very much on that part. I missed that. Let me make that a little more clear. So I just copied it down wrong. Got a little ahead of myself. So we had 1 plus x e to the 2x right there in that last position. So yeah, make sure you notice that as well. So, but yeah, in terms of what's going on here, you do not have to show all these steps. I think this is a lot of extra work. Hopefully we can get where you can do a lot of these without needing what's on this left-hand side, right? Hopefully those become where you work the problems enough, you just kind of know them. I'm just putting them out there for those of you that don't, just in case, so we have some form of derivatives that, where did these come from? Okay, next problem, another derivative, I bet. Ooh. Find the derivative of g of x equals 4 times cosine x in the numerator, and then divided by the natural log of x squared minus 7. Okay? So, when we take a look at this piece, what's actually happening? Well, when we want to take this derivative, we're going to need a couple components that we need to know the derivatives of. So I'll put the derivatives that we need to know on this list here. We need to know the derivative of cosine of x. Okay? Derivative of cosine of x, that's going to equal just negative sine of x. And what about the derivative of natural log of, and I'll just put x right now. We can deal with that in a minute. That's going to be 1 over x. Okay. The other piece is we have a quotient. So you have f of x divided by g of x. And so what is the quotient rule? This is a little bit more interesting. You take g of x, the quantity squared, and then we'll go write g of x up here, and then times f prime of x, minus, you write the numerator, f of x, and then times g prime of x. One way, actually, I learned how to memorize this. The easiest part, I think, in taking that is to remember that you square the denominator. And so what my teacher always told me a long time ago in a land far, far away is that after you square the denominator did some work, so you just let it rest up top. And so that's why we have the g of x. And so now the numerator is ready to do some work. And so that's why you get an f prime of x. It's the derivative of f is just f doing some work. Then the numerator and denominator don't like each other. That's where the minus sign comes from. And so since the numerator just did some work, we let it rest, and then the denominator is ready again to do some work, and that's why we take g prime of x. So that's where it kind of comes from. And so I see another question up there. I'll answer that after we finish this problem. So kind of moving forward from here, these are our main components. Where do we go from here? Well, we get g prime of x equals, well, the first thing to do is just square the denominator. So I'll put that in brackets just to kind of make life easy. Natural log of x squared minus 7, that whole quantity squared. Now we rewrite, so rewrite the denominator, natural log of x squared minus 7, times the derivative of the numerator. So the derivative of the numerator, we have a 4, right? Constants, they won't play a factor, we just leave that factor out, and then times the derivative of cosine of x, which is just negative sine of x. Okay. Then remember, numerator and denominator don't like each other, that's why there's a minus sign. And so we have the numerator now at f of x, so that would be 4 cosine of x times our derivative of our denominator. Now this is where things might get a little bit tricky. What's natural log? Well, it's 1 over x, but we don't have an x, right? We have an x squared minus 7, so we put 1 over x squared minus 7. Anyone know what we have to use? So hopefully you were thinking it in your head, we needed to use the chain rule. So that's the derivative with respect to x of the interior function, so x squared minus 7. So now where do we go from here? Well, we have natural log of x squared minus 7, the quantity squared, and then we have natural log of x squared minus 7. Don't let your eyes fool you, that's a perfect square right there. And times 4 and negative sine x, I'm just going to put that negative symbol right there, right out in front. Most of the time I'll pull the 4 out in front as well, but for right now I'll just leave it right there. Minus, so 4 cosine of x times 1 over x squared minus 7. Don't let your eyes fool you, that's a perfect x squared minus 7. And then times the derivative of x squared minus 7, we just use the power rule. I didn't write that over here. If you don't remember the power rule, d dx of x to the n is n times x raised to the n minus 1 power. So that's where the 2 drops down, and we subtract 1 from that exponent. So where do we go from this piece? Well, you can leave it like this most of the time unless there's something that has you put it in a certain format. I usually don't ask for that myself. That's just someone else is doing. But if you wanted to brush this up, what we could do is, you see that denominator, and I'll kind of circle it right there, at 1 over x squared minus 7. So what we do is we multiply every term by x squared minus 7. So what that does is that would put an x squared minus 7 times natural log of x squared minus 7, the quantity squared. We need an x squared minus 7 here, but notice we also have a negative 4. I'll pull the 4 out in front finally. Negative 4 x squared minus 7, we multiply by this term, times natural log of x squared minus 7 times that sine of x. And now that 1 over x squared minus 7 is gone, so what we're left with is just, notice we have 4 and a 2, right there. And since we multiplied every term, 1 over x squared minus 7, that's gone. So we have 4 and 2 makes 8. We'll pull the x out in front so it doesn't look too funky. 8x cosine of x. And so that would be a final format. So I see some comments, and I'll try and address them one by one as I can. So yeah, I heard the low d high minus high d low over the bottom square. That's great. That works just fine. And what's happening here, so some people call this low, and some people call this high. So high and low. And so what we see here is low d, meaning derivative of high, minus high, and then d low, and then all over, let me put low, spell it correctly, all over the low squared. And yeah, that's exactly right. Whatever gets it, so you have it memorized, that is awesome. I'm all for it. So another question that we had, are we supposed to know how to calculate e, the value of sine, cosine, and tangent? Well, yeah. So e, you can just leave as e to the whatever power it is. Sine, cosine, and tangent, there's main angles that you should know on those. So with the sines, cosine, and tangents, if it's just an x, you just leave it as is. But if you have, say, sine of pi over 2, you might have to go back to your unit circle and know how to do that and things of that nature. So just kind of keep those in mind. There's some angles you should know off the top of your head, but let's say it was sine of 3 pi over 7. Which that isn't a common triangle that we are supposed to know or anything like that. Just leave your answers sine of 3 pi over 7 or whatnot, or unless it says, hey, use a calculator. I know some of you will be using a calculator, some of you won't, so just kind of FYI. Use it if you have it. If you don't, just leave it as that answer, and you should be fine on those type of problems. Okay, so moving forward on this, let's see our next one. What do we got? Ooh, this one's all sorts of nasty here. Find the derivative of r of x equals 3x squared sine of x square root of x squared plus 1 in the numerator divided by 9x plus 1, that quantity raised to the 10th power, and then the secant raised to the 7th power of x. Oh my goodness, this is all sorts of nasty, right? And some of you might be saying, oh, we're going to use a quotient rule and a product rule and a chain rule and all that jazz. Yeah, that might seem away, but this is a great example of where logarithmic differentiation can come into play and make your work a lot easier. So I wanted you to see a problem. That's why I'm putting this one up here, showing you how the logarithmic differentiation can cut down on your time quite a bit. I'm not saying you have to use it. It'll be a lot simpler format. So let's take a look as to what happens here. So in terms of logarithmic differentiation, what do? First, we take a logarithm of both sides. So you take a natural log equals natural log of, all this junk. This does not look fun. 3x squared times sine of x times the square root of x squared plus 1 all over 9x plus 1 raised to the 10th power, and then we have a secant to the 7th power of x. Okay, where do we go from here? Well, the reason we have this idea of a logarithm is to break this problem down and make it easier for ourselves, right? What are some of the properties of logarithms? So you have all these things, the product rule for logarithms, and I'm not talking derivatives product rule. You have a product rule, a quotient rule, and a power rule for logarithms, which allows us to break this apart. And how can we break this apart? Well, you have a natural log of r of x, right? Anytime you see multiplication of anything up here, doesn't matter what it is, you can break it up with a plus. And if there's a division, the stuff in the denominator will have a minus in front of the natural log. So what do I mean by that? Well, you can break this up as natural log of 3, which is just a constant, by the way, plus natural log of x squared, which we'll come back and talk about how to break that down further, plus natural log of sine of x, plus the natural log of the square root of x squared plus 1, minus the natural log of 9x plus 1 to the 10th minus the natural log of secant to the 7th of x. Okay, so this does not look pretty, I'll admit, because it seems like we have more terms. But what we're going to do, we're going to make it a little bit simpler for ourselves, and that's properties of the logarithms, and that's especially the powers. Remember, this square right here can go right down out in front. This square root symbol is raised to the 1/2, so that can go down out in front. This 10th power can go down out in front. This 7th power can go down out in front. That's just the power rule for logarithms. And what we'll be allowed to do is take the derivative with respect to x now of both sides. And what's actually happening, I know you don't see a y, but technically this is going to be an implicit differentiation, so we'll show how that works. So we have a d dx and then the derivative, and I'll just put it all in brackets rather than write all those multiple d dx's, meaning we're going to take the derivative. But you can keep in mind that each piece we can break across with the sum. So you have plus, our next term is 2 natural log of x. Well, that looks pretty simple, right? Plus natural log of sine x doesn't change. But this bit with the square root does. Remember, the square root is that whole quantity raised to the 1/2 power, so we can pull that 1/2 out in front, and we're left with natural log of x squared plus 1. Now we have minus 10 natural log of 9x plus 1, and minus 7 natural log of secant of x. Okay. Welcome to implicit differentiation. So what happens here? Well, when we take the derivative, you have r of x. So natural log of r of x, we go 1 over r of x. Right? That's just the natural log part. But times r prime of x. Okay, because we have to take the derivative of the inside function. So we are going to have to do some work to find r prime of x at the end of the day, but it shouldn't be too bad. So now, the next piece, we have natural log of 3, which is, that's just a constant when you think about it, so the derivative of that is just 0. Plus 2 times, the derivative of natural log of x is just 1 over x. The derivative of sine of x, so I'm going to pick up the pace a little bit compared to the other ones. When we do this, we do the 1 over the inside function, times the derivative of the inside function by the chain rule. So I can write the d dx in sine of x, but the derivative of sine of x is just cosine of x. Okay? If I end up losing anybody, just let me know, and I'll try and slow it down and kind of brush up that step. Plus 1/2. Okay, natural log of x squared plus 1, that's going to be 1 over x squared plus 1. Right? Times, well, derivative of x squared plus 1 is just, well, the derivative of x squared is just 2x by the power rule, and the derivative of 1, that's just a constant, so that's 0. So that's just 2x. Minus 10 times, well, it goes 1 over 9x plus 1. Times, once again, the derivative of the interior function, 9x to the first power, so you can drop that 1 down, this becomes x to the 0, so essentially you get just 9, and then derivative of 1 is 0, so you get 9 all together. And then minus 7 times 1 over secant x. I'm running out of room here, so I'll do my best to fit it. And since it's multiplication, here's what I'm going to do to make it fit. I'm just going to put it in the numerator. Since we're multiplying, that isn't going to make a difference where it goes. It always goes in the numerator. Derivative of secant x is just secant x tangent x. Okay? Now, moving forward from here, what are we trying to solve for? We're trying to solve for r prime of x. So what we get is r prime of x equals. This looks all sorts of nasty, but we need to multiply both sides by r of x. So I'll put r of x right here. And we'll do a big old parentheses to indicate all this. So 2 times 1 over x, we can rewrite that as just 2 over x. Okay. Cosine of x, so when we're talking this, cosine times 1 makes cosine of x over sine of x, and that is just cosine over sine is cotangent of x, I believe. And then notice in this next piece we have the 2's will cancel, so we have plus x over x squared plus 1. And by the way, all this simplifying is not necessary once again, so you don't have to have cotangent of x and all that jazz. I take all sorts of different answers as long as they're available. So notice we have 9 times 10, that makes 90, I believe, over 9x plus 1. And then minus, notice you have the secant x's will cancel, and you're left with 7 tangent of x. If you actually wanted to make your life a little bit easier, by the way, you could have done that right from the get-go. So just a little FYI, when you had secant to the 7th of x, notice that's 1 over cosine to the 7th of x. So you could have actually taken that and make it cosine up in the numerator. So that's where the tangent kind of came from. Then that's why things canceled out the way they did. So there's more than one way to skin a cat here is essentially what we're getting at. So now the last piece of this puzzle, what does r prime of x equal? So r prime of x equals, well, we need r of x times all this. What the heck is r of x? Well, if you look, we have right out the gate r of x equals all that junk. So notice this is 3x squared times sine of x times the square root of x squared plus 1. 9x plus 10, or 9x plus 1 to the 10th, and then secant to the 7th of x, or as I mentioned, you could make the cosine to the 7th power of x up in the numerator, times all the stuff we just wrote, so that's 2 over x. Hopefully I can copy this part down right. Cotangent of x plus x over x squared plus 1 minus 90 over 9x plus 1 minus 7 tangent of x. Okay, so had a few questions pop up along the way. Yeah, so depending upon which class, when I went to schedule my exam, the lady told me that we could not use a calculator. Is that true? Depends which class. So if you are in the Armstrong class versus an E-Core class, those are the two classes I'm teaching right now. The Armstrong class, you are not allowed to use a calculator for this exam, and that is true. So that means the good news is you don't have to spend all your time simplifying and doing all the extra algebra for that. If you have an E-Core class, then you are allowed to use a calculator, so keep that in mind. But so for the Armstrong class, you do not have to use a calculator, so you are not expected. If you have something like the square root of 117, leave it as a square root of 117. So there's no reason to worry about that. Okay, so the next question. So will we be able to find the derivative of every function with the logarithmic technique instead of using all the other rules like the quotient and product rule? Yes, in fact you can. Just sometimes that might take a little more time.